So far, we've seen liquid chemical propulsion, where a liquid fuel and a liquid oxidizer are combined and combusted. There's also solid chemical propulsion, where the fuel and oxidizer are mixed and stored in a solid state. When we talk about solid propulsion, we use the word motor instead of engine. In a motor, the combustion chamber is elongated. The propellant or fuel oxidizer mix is stored in the combustion chamber. For larger motors, it's usually molded or cast in pieces and afterwards assembled. Between the combustion chamber and the propellant lies an insulation layer to protect the combustion chamber from the extreme heat. The simplest shape of the solid propellant is a cylinder with a hole through the middle. The hole is named the perforation. The burning starts on the surface area of the perforation and expands outwards. There are many shapes, also known as grains, that the solid propellant can be stored as. The surface area of the grain at any instant is proportional to the thrust. This is why different grains have different thrust to time curves. Thrust that increases over time is called progressive. Thrust that decreases over time is called regressive, and a constant thrust is called neutral. The area under the curve represents the momentum gained by burning the propellant. The thrust is also proportional to how fast the propellant is burning, also known as the burn rate, expressed in millimeters per second. The burn rate varies depending on the pressure inside the combustion chamber. The higher the pressure, the higher the burn rate. The pressure inside the combustion chamber is determined by the nozzle's dimensions. An electrically activated pyrotechnic device is used to commence the burning of the motor. Solid propulsion has a number of advantages and disadvantages. A major advantage is that it generates a larger thrust than similarly sized liquid propulsion does, albeit for a shorter period of time. It's also simpler than liquid propulsion. This makes it cheap. The thrust per cost ratio is high. The thrust can't be actively changed during flight. Once ignited, it will burn the way it was designed to burn. You can't push some button and decrease the thrust by 10%, as is the case with most liquid chemical propulsion systems. Solid propellants are usually not as efficient as liquid propellants. Physically, this means that the velocity of the exhaust gas is not as high as with liquid chemical propulsion. There are no cold liquids to cool the nozzle. In liquid propulsion, the fuel is often used to cool the nozzle to prevent decomposition and for saving weight. Not having this ability is problematic for solid motors. Active thrust vectoring, actively controlling the direction of the thrust, is also difficult. The nozzle of a solid motor has a really tough job. It has to withstand extremely high temperatures without any cooling. How does it do this? It relies on the energy required to heat up the nozzle being as large as possible. In other words, materials with a high specific heat are favored. Since the motor only needs to operate for a few minutes at most, this helps. It also uses materials that require a lot of energy to decompose. Insulation is used so that the rate at which things heat up decreases. A throat insert can be used in extreme circumstances. A throat insert is usually made of a high-grade graphite. It has great properties at the extremely high temperatures it will be heated up to. The gas at the throat might not be the hottest, as you've seen in the second episode, but it is the point where heating is the largest, due to the small circumference. Here we have a graph showing the heating per unit surface area throughout the nozzle. Some throat inserts are made of tungsten. Tungsten has an incredibly high melting point and is very resistant to decomposition. On the downside, it cracks easily and is heavy. After a 2-minute burn or so, the nozzle will have lost a significant amount of material due to decomposition. A few inches of thickness is definitely possible for a large solid motor. How much was lost largely depends on the material and its location in the nozzle. Solid rockets have been around since at least the 13th century. However, they still have their place in our society today, even in the commercial space sector. Let's look at some examples. The Atlas V is a rocket currently operated by United Launch Alliance, or ULA for short. This rocket uses what are called strap-on boosters to increase the delta V without adding too much cost. These are smaller solid rockets that provide some additional thrust early on during the mission. They are jettisoned after they run out of propellant, which only takes 94 seconds in case of the Atlas V. For comparison, the first stage's engine operates for 253 seconds. The Atlas V can utilize up to 5 boosters. The Atlas V boosters have a diameter of 1.6 meters, which is large, but there's much larger. Here we have the Ariane 5 rocket, a rocket operated by Arianespace. Now we're no longer talking about strap-on boosters, because the Ariane 5 has to use these. These boosters have a diameter of 3.06 meters. One of these provides almost twice as much thrust as the Atlas V's first stage liquid engine does. Remember that motors provide more thrust than similarly sized engines do, so this shouldn't come as a surprise. We'll also look at the Vega rocket, another rocket operated by Arianespace. This one's pretty unique. It has 4 stages, the first 3 of which are completely powered by solid motors. The 4th stage burns a hypergolic fuel and oxidizer. Hypergolics don't need to be ignited. They ignite as soon as they come in contact with one another. The Vega rocket is quite small compared to the others mentioned in this video. It is intended for small payloads only. Nonetheless, it hasn't failed a single time. And lastly, we have the Space Shuttle, of course. The Space Shuttle's solid boosters have a very difficult task. They have to carry a giant tank and a giant space plane off the launch pad. The Space Shuttle itself doesn't generate all that much thrust, so it really relies on those boosters. In the next episode, we'll be looking at hybrid propulsion. This is where one propellant is solid and another is gaseous or liquid. Thanks for watching. The sources for this video are in the description. I have a Patreon account in case you'd like to support me. I share all sorts of stuff there. Feel free to like and subscribe if you learned something. I'll see you next time.
So this is a model of the booster.
Okay.
What am I looking at here?
This is a model of the SLS booster. What you're looking at, the top end, if this was stacked vertically, this would be what's at the very top. Here's the nose cone, and this is what we call the forward skirt. And inside this forward skirt will be all sorts of avionics boxes, the control systems for this booster, as well as they integrate to the core stage of the vehicle. Starting from here down, what we call these are 5 segments of the solid rocket motor. This is where you see the propellant is. So this is 12 feet in diameter, and most of it's propellant. You've got a bore or a hole going down the whole entire length of the motor. So right here by my finger up in the front end, though, you have a little what we call the igniter. It's like a small solid rocket motor itself that ignites and shoots a flame down the full length of this booster, or 150 feet of propellant, and it ignites all the surface of all the propellant at once, so that it all starts to burn together. At the very end of this booster, you've got what the nozzle, and the nozzle is where all the flame and the mass is coming out producing your thrust. And surrounding that nozzle, you have what's called the aft skirt that protects the thrust vector control system, or the big actuators that can steer this booster by moving the nozzle.